pleasure to introduce Arno Solin's talk. Okay, Arno is a professor at Aalto University in Finland, and the floor is yours.
Thank you. I hope you could hear me. Yeah, some nodding in the back row. Great. I put a cat here so that it's absolutely clear to everyone that this talk represents the machine learning perspectives and not the stat perspectives. So this is maybe more applied than the other talks, but I really like the previous talk we had just before lunch, because I think many of the kind of more maybe kind of background concepts were very well presented there, and now I can focus on the cats. So yeah, I'm talking about fixing uncertainty, and that sounds a bit grand. And spoiler, I'm not actually going to fix anything or solve anything, but hopefully I'm trying to improve things in practical sense. Let's start with an icebreaker, because, well, it's afternoon after all, I have just had lunch and so on. So this is an old picture I generated many years ago when first diffusion models that actually could generate conditional samples with prompting came out, and I wanted a picture for talk. I wanted to have old meets new, like horse meets Tesla. Who has a Tesla here? There's at least some. Good. Who has a horse? Don't laugh, because my empirical finding is that there's typically more horse owners in the audience than Tesla owners. I find this a bit weird. Who noticed that the horse has 5 legs? And I think that's kind of summarizing things really well with these kind of deep learning models that might be really impressive, good at generative tasks, good at all sorts of things, kind of impressive things like human-like AI. But then some simple things like kind of learning that animals typically have an even number of legs still seems to be tricky. And I think this is just like a sign that these models, they don't really learn in the sense that humans learn, and there's a lot of complications actually to them. And I think there's probably many reasons for this particular case. It's not the lack of data in this case. Well, someone once pointed out that often horses, they tend to like other horses. So they might stand next to each other, and then it might be hard to count the legs, when you fit the flexible function to it, and so on. So there might be many reasons to it, but this is just like a motivating example that there's more to these models than meets the eye. Okay, I think it was 7 years ago, I attended a talk in that building, just there behind, and Neil Lawrence, who some of you might know, he gave a really good kind of introductory talk on what machine learning is. And I don't really remember exactly how he put it, probably much better than I can, but he kind of had this idea that machine learning is built out of 3 parts, 3 ingredients. And well, the first one is data. You need to learn from something, observations, not. And the second thing is models. And that's basically where the person who is designing the machine learning method kind of is encapsulating the prior beliefs of what is generating the data or what could be explaining the data. And then he had this a bit fuzzy last ingredient, kind of the secret sauce that brings the meat and the potatoes together, kind of. And I don't remember what he called it, and I'll just call it algorithms here. And that's kind of all the rest, the kind of the dirty details, be that then scoring rules or whatnot, how you train the your method, how you infer things about future unseen examples and so on. And well, I think many of the things that have been discussed in the talks this week might have been more on kind of what I would put under algorithms here. And why is that? because often the models, especially in like statistical sense, there's a lot more clarity to that, kind of. I visited some posters the day before, and I really liked how many of the posters presented a very clear description of the model, because the phenomenon that was being modeled was kind of well understood. You had a lot of like prior knowledge of the problem, a lot of prior knowledge to encapsulate into the problem, so that you could then infer things about it and so on. And well, in machine learning, the models, that's a bit of a more difficult case in many modeling tasks, because you don't actually know that much about the problem. If I were to model some physical phenomena, I build a model of a magnetic field, I would take out Maxwell's equations, and I would use that as strong prior, and then I could kind of build my model around that. But if I'm actually like interested in modeling how cats look in images, I don't really know how to write an equation that would describe cats. And that's why we need all the flexibility that we typically use in all these deep learning models. I'll go to that in a bit. So, okay, that's like a long intro to what I'm planning to talk about. So I'm actually talking about 3 papers, all of which are actually with my former student Lassi Meronen, who already left the nest, so to say. But I really like these projects, and these already start to be quite old. Like there's a nearest paper for 2020, like a follow-up paper from 2021, and then a paper from last year actually. And I'm really like looking at kind of, if you think of this thing, I'm looking at kind of the modeling aspects first, and then in the third paper, kind of the inference things. And what these are about, we'll go into in a bit. And there's a lot of other people as well involved, not only Lassi. There's been a lot of co-authors who have contributed to these things. Some of them have left or are now working at other places, but then, for example, Andrea here helped a lot with kind of actually computational aspects, because, well, machine learning, especially deep learning in big models, that's a lot more than equations. It's also a lot about how to implement things. Good. So I'm first talking about the modeling part, because that's actually quite crucial, and we'll get to how this kind of relates to uncertainties and so on. So kind of in statistical machine learning, and I guess in statistics, we typically like to put a lot of prior knowledge into things. And I'm a big fan of Gaussian processes, and I'm happy that the previous talk actually like gave an example of Gaussian processes. And I think that's a good example of kind of a non-parametric modeling paradigm, where you can like include knowledge about latent functions. Well, there's many ways how you can do that. Typically, machine learning, we compose a kernel that encapsulates what we believe. And kind of in statistical machine learning, we put a lot of focus on that. And often, like, the problems are such that we know a lot about the things that we're modeling. And then there's the deep learning community. So whereas the first cat here is carefully measuring things and putting things in place, the second cat is kind of cooking. And you know, some of you have tried like vibe coding. So this is like vibe cooking. So like you throw in things and you try a bit and see how it works. And deep learning, kind of modeling deep learning is pretty much like that. And that's said with all respect. So Yingxin Li, a colleague of mine, once put it very nicely that deep learning is like traditional medicine. So many of the practices you have in deep learning are not based on some like rigorous research and derivations. It's more like people have tried different things over generations. Well, in traditional medicine, generations span hundreds or thousands of years. Whereas then in the deep learning community, a generation is perhaps like a PhD student generation. So that's like, I don't know, 3 to 6 years. And people have found ways how to do modeling. So you kind of know that, well, I'm building a generative diffusion model. And then you kind of know that, well, what sort of unit and what kind of tricks you should use for actually getting it to work. Or then if you're building an image classifier, you kind of know that, well, you should use all these tricks and all these like structures in your model for it to work. And that's kind of then like, kind of partially like quiet knowledge that goes from person to person or GitHub repo to GitHub repo, but that's basically how it works. And I'm not saying it's bad, it clearly works, and the results that the deep learning community have come up with, they are impressive. I think we can all agree on that. So it might not be a bad way. But of course, we would hope that at least kind of in retrospect, someone finds out some more theoretical reasons and guarantees why certain things are the right ways to do it. And that's kind of what I'm kind of aiming at here to build like links between model families. Good. Okay. So what I'm aiming at here is to model what happens outside data with all these fancy cat images and so on. So this is kind of what it boils down to. And so I have some data set, some training samples, and basically I'm interested in predicting stuff that might be OOD, outside the training data, or otherwise different from what I'm training on. And I would like that the model to be kind of aware of its own uncertainties when it comes to that. And here on the left, I have a simple neural network model with a rectified linear unit as an activation function. And it basically, choosing that model structure induces a prior on the model functions, that's what they can represent. And what you see here is that the model here is on the left, it's very kind of certain about things. Kind of the predictive uncertainty, like the marginal uncertainty here is kind of visualized by the color, background color here. So the lighter the color, the more certain the model is about itself. So for example here, the model is very certain that it should predict the points to be of the orange class here, and up there in the corner it's very certain that they should be of the blue class. Well then, if I would use a Gaussian process prior, a stationary Matern 5.2 or some other prior for the Matern class, I would end up with something like this. And there basically, when building the GP model, I'm quite explicit about things that I want to happen outside the data. And then I also get that. So here, for example, this color here is a lot darker than it was there up in those corners. And it's certain where there's data, and it's uncertain about the class. It's still predicting like the orange or blue class, but it also says that, well, here, it's outside the training data. I don't really know. And that's the kind of behavior that I would like to see in neural network models as well. So, in brief, I would hope that I could have similar behavior as with GPs, in this case, in the neural network model. And then in other terms, basically, if I would have like cats and dogs and horses, and the model would only have seen cats and dogs, then it basically should be uncertain what to classify the horse to. Or then, if it would see a car, then that's kind of completely out of distribution when it comes to animals, for example. So then, instead of having something like this, I would like to have something like this that would kind of know that, well, I don't really know what happens when I'm outside the training data. And this might sound kind of easy, but now, as we saw in the very first example with the Tesla and the horse, when we're working with, for example, images or text, the models are actually very complicated. It's not so that I can actually plot these things and say that what's outside the data, so on. So then that makes this quite hard when it comes to modeling and inference. If you're not familiar with GPs, I have this one slide on Gaussian processes. So Gaussian processes are a non-parametric machine learning paradigm where you typically then, like in kind of canonical machine learning form, you overpresent the model in this way. You have some latent functions f that you put the GP prior on. And the GP prior is fully actually characterized by its covariance function. That's a kappa function there. And typically you might impose prior beliefs about model functions. You might assume that they are continuous, they are differentiable. You might assume that they have some periodic structure, or then you might have something much more complicated and clever. But these are kind of standard things. And then you have a likelihood function that then is, like in this case, factorizing over the observations, and that couples your latent functions f with your observations y. And in probabilistic machine learning, this is kind of a nice way because it kind of separates out the likelihood and the prior, and then you actually impose assumptions about the functions, how they should behave. And then in neural networks, even if kind of the machinery would allow for something similar, that's not how the community in deep learning sees these problems. So it's more than that we have this very opaque kind of box where you put in stuff from one end and you get outputs from the other end, and then you kind of hope that you can train the parameters so that you explain the training data. And I was asked to put in some like basic things about neural networks as well. So in simple terms, a neural network is a parametric model that is consisting of these like artificial neurons, you can call them, where you have some inputs, you have some parameters or weights, you sum them up, and then to make sure that it's not a linear model, you need to have some nonlinearity there, and that's basically the activation function that is some nonlinear function. And often if you take out a deep learning book or, I don't know, deep learning blog post, you might say that, well, it doesn't really matter what sort of nonlinearity you have, as long as it's nonlinear. And that's kind of true because, well, clever people in the 1980s showed that, well, if you have nonlinearity there, it's a universal approximator. But then actually it plays a big role what kind of nonlinearity you have. And that's what most of the remainder of the talk will be about. So then the nonlinearities that people typically choose might be like a logistic function, hyperbolic functions, or a rectified linear unit, or then if you have followed what happens in LLMs, they have a lot of custom activation functions that have been tailored for the LLM use case. Often they look like ReLUs, but they are actually differentiable, they are smooth. There's no like hard edge there. And that has empirically been shown to be a good choice for LLMs. Good. So then we can stack these nodes and build layers of them, and then we can stack layers to build deep models as well. I'm mostly focusing here now on single hidden layer models for a good reason. The interesting thing for someone who loves GPs is that Bradford Neal showed in the 90s that random untrained, basically, single layer feed-forward network, this form, actually converges to Gaussian process in the limit of having like infinite width, or like infinitely many neurons. That gives you a Gaussian process. And if we now denote the activation function with this sigma, we can actually, like, if we look up Bradford Neal's PhD thesis, it's actually very nicely written. We can recover this integral that kind of gives the relation to the associated kernel in the infinite width network. Good. So then, in some cases, when you take a widely used activation function in a neural network, and then you stack an infinite number of those, basically take the limit, you end up with a nice closed form kernel representation. And that's pretty cool. In many cases, though, there's no closed form solution, but then you can still approximate this by basically like a Monte Carlo approximation of the integral on the previous slide, where you then sample random weights and biases from prior, and then recover and approximate, basically can evaluate the Gram matrix that gives the covariance structure that the network imposes. And now if we look at different neural networks, for example, if we would have a step activation, that's also a nonlinear function, and then we can then derive the kernel for a closed form. That would give something like a arc cosine 0 kernel based on prior work. And then here, this is a small network, I don't quite remember, maybe 30 units or so. And then in the infinite limit, then under us doing then like GP inference, this would be the corresponding Gaussian process model for the step activation. Or then we could use ReLU, and also there we can recover it in closed form. And here's like a finite width neural network, and that's an infinite width Gaussian process with the same prior. Or then a sigmoidal activation, that would give us that sort of a Gaussian process solution. Or then with the radial basis function, we can also do it. A radial basis function is also a nonlinear function, and we can recover the neural network, the Gaussian process that corresponds to the infinite width neural network. But then, if we think of going the other way around, so probably the most used kernel family in Gaussian processes is the Matern family of kernels. That is, if you open up a textbook on Gaussian processes, it probably suggests you to use a radial basis function kernel, or then some lower order Matern variant that is stationary, and then encodes your model function should be continuous, and once or twice or 3 times differentiable typically. And there's a bit of a question mark that what would be the corresponding activation function in a neural network that would correspond to this. And it's probably a good class of covariance functions, if that's the most widely used covariance function family in Gaussian processes. And Gaussian processes are well known for being able to capture uncertainties, and people are typically quite fond of these models. But then it's a bit weird that it has been a bit overlooked in the past decades, that what would be the corresponding activation function that could give you a neural network that would behave in this way. And that's what we looked at. So we looked at locally stationary models that would be like a priori encoding stationarity into neural network models. And typically people have looked at, well, you take your neural network, it has some activation function, what is the corresponding GP kernel? And we basically went the other way around. We took a family of GP kernels, and we are asking that what would be the corresponding activation function that would give that. And it turns out that there's probably a reason why people did not do this in the 1980s, when this was also like neural networks were hot then, and people actually maybe had more of a signal processing background to these things back then. So there's a lot of people who were very well versed into transfer functions and spectral densities and so on. But no one really cared about the Mattern family in neural networks in the 1980s. So the RBF, the radial basis function, or the Gaussian kernel, has been analyzed extensively already in the 80s and 90s. And the RBF, so if you take the RBF kernel and assume a Gaussian input density, then the eigenvalues, eigenfunctions associated with the covariance operator, they're actually available in closed form. And this makes it actually quite easy to derive then the connection between an infinite width neural network and a corresponding kernel. This is not possible for the general Mattern family, because then you would need to derive the Green's function, and this, at least I tried it, and it was very hard. So instead, what we did was that we took more like a signal processing or like a control theory route to solving the problem. So the stationary Mattern family covariance functions, this is the general form, and there's basically a length scale, characteristic length scale parameter, it's the L, and then there's this new parameter that tells about how many times differentiable the model functions would be. So this is kind of the general form. It's rarely used in this form, often used in a simplified form. And the so-called Wiener-Khinchin duality gives the corresponding spectral density for this, which is a lot simpler and actually quite convenient. And this is actually nicely factorized. We can factorize this into the following form. So that's called spectral factorization in signal processing. And we can then we can read out what the so-called transfer function of the corresponding stable part of this spectral factorization is. Basically the G there. And the remaining kind of all the kind of constants have been conveniently collected into that Q there, and looks a bit hairy, but it's just a constant. And it's good to keep that with us, because that then makes it possible then to actually make the scales match between the Gaussian processes and the neural network later on. So now, still from the signal processing community, we can then use the basic tricks and that is used in control theory. We can take an inverse Laplace transform of this, and that actually gives us the transfer, or so-called activation. And people might be kind of unaware of this, but then if you think of what Gaussian processes are, typically in machine learning, we like to think of Gaussian processes in terms of kind of the kernel formalism, that we have some sort of moment representation of the Gaussian process. But there's many alternative ways of working with Gaussian processes. Often in spatial statistics, people might consider kind of these filtrations, that you have kind of a Gaussian random field, and then you apply some sort of linear operator to that, and then that's kind of how you recover your priors, or posteriors for that matter. And this kind of is very similar, because what the transfer function does is that you have this kind of white noise process, you could think of that kind of informally as a Gaussian, and then you apply a filtration to that transfers that into something that you're interested in. So that's very much related to then having a random neural network with Gaussian weights that you then apply some sort of then like filtration on. And that's kind of the activation that happens. So the intuition is there that it makes sense. And this was kind of then like, if we go back to 1980s, this was how people actually, like a lot of people viewed neural network models. And that's kind of things that have been maybe partially lost. The kids these days don't think of these things anymore like that. Yeah, that's basically what I said. So then you could think of it as a filtration kind of on like a Gaussian field. Okay, so we actually recovered here in the process a family of activation functions. But then it's kind of under the assumption that there is kind of a Gaussian decay envelope, kind of a input density that we are being assumed on the inputs. And that's typical for many of the other like connections between neural networks and Gaussian processes as well. Then that of course also boils down to what sort of priors you assume that you have on your parameters for your model. So what do the activation functions look like? They have this weird form, look like this, and here you can see then for different Matern kernels that what they would look like, and they look a bit funky, and they might not actually be that convenient in the end. But let's see. And here I've like evaluated the model. I have like this like Monte Carlo approximation to the original integral, and I can actually see that. I don't know if you can see it here, but then there's like the exact covariance, and then like there's a dashed line, and then the evaluated approximation, which actually match really well. And these are with other priors. So now again, if you go back to the deep learning community and ask that, are these kind of good activation functions? There are these like usual checks that people have, because in theory you could use any nonlinearity. Typically you want activation functions to be monotonic, because someone showed at some point that guarantees that the error surface would be convex. Well, they are not monotonic. Also, it's kind of bad that they saturate to 0 for most x. It could be hard to optimize. Well, they're mostly differentiable except for the exponential, that the nu equals half. It can also be tricky. So they aren't ideal activation functions for neural networks. But let's not let that disturb us if we can actually try them out in practice. That was kind of locally stationary functions, which had like assumed an input density. And the follow-up work that we had also considered then, and these are the locally stationary, and then also considered then like globally stationary activation functions. So you can see that the effect of the input density makes things like die out when you move outside the envelope, kind of. So well, then for globally stationary activation functions, that would not be the case. So these would be examples of the Matern and the RBF under local stationarity, and then these would be examples of both the Gaussian process and then the corresponding neural network with an activation function under then global stationarity. And now like the top row has basically infinitely many nodes, while then the bottom one has, I think in this example we used maybe 20 or something. So it's a very small neural network. So even if it should only hold in the limit of infinite width, we can see the effects actually with very small networks already. So the catch is that for the global stationarity, we can again use the Wiener-Khinchin theorem that couples the spectral density with the covariance. and establish a link between periodic activation functions, those are also nonlinear functions, that then give a representation of the globally stationary model. And then what I mean by periodic, I actually mean that basically any sort of periodicity is okay. We shouldn't be too picky with the activation functions. The deep learning community is very accepting as long as they are nonlinear, and turns out that even in the experiments we did, it didn't really matter what sort of periodic function you used. A sinusoid is of course nice because you can differentiate through it, but then even this like periodic ReLU, this kind of this like piecewise linear function, that worked great, really fast to evaluate, very convenient. And then the catch for the globally stationary ones is that then you kind of tune the class of like the Mattern class basically by considering different priors on the weights. So Cauchy distribution gives you an exponential kernel, a student t, then like the general Mattern kernel, and then the limit and the standard normal distribution, the RBF. Okay, some examples, because I'm sure that you're actually convinced that this is useful in any way. There's a sanity check. So basically, these are the globally stationary functions, and compared to the kind of the exact covariance, and yeah, the triangle wave and the periodic ReLU, they are all overlapping basically with the exact one. So at least the prior seems to match. We did this like kind of standard Bayesian deep learning experiment where we trained a small neural network on the normal MNIST digits, and then we evaluate on rotated digits that the model has not seen during training. And that's kind of then like, because we can then start by just rotating a bit and then keep rotating more and more. That kind of should correspond to kind of moving further away kind of outside the training distribution. And if you use the ReLU model, that's the blue line, it works equally well in terms of accuracy as all the other activation functions. But the interesting thing is that what happens then when we evaluate confidence or negative log predictive density on the test set. And then we actually see that the ReLU model is super confident about what it does, and it's also quite wrong. So the stationary activation functions actually help a lot with being uncertain outside the training dataset. We also ran experiments on like small scale UCI regression tasks. That's maybe not that interesting. We evaluated on images. We trained on the CIFAR-10 dataset. It consists of these small images that come from 10 different classes. There's like some animals and airplanes and things. And then we tested both on the test set of the CIFAR-10 dataset as well as on the test set of the CIFAR-100 dataset that just has more different classes covered. And then on the street sign dataset that is kind of more out of distribution compared to the CIFAR datasets. And here, down here, you can see then test set examples ranked so that those that are according to the model more similar to the test set, basically based on predictive entropy. And the nice thing is, I don't know if you really can see it here, but there's more examples in the paper, that these most similar to the like training data set, like so then they are typically images that make sense, kind of sharp images where it's clear what is in the image. Well then, these that are least similar are more obscure. I have no clue what this is. This is a chair, but I don't know what this is. I don't know what that is. I have no clue what that tries to be. And the same then for these out of distribution samples that clearly show as being out of distribution. That's the bump here basically. So the model actually realizes that these are different from what it has seen during training. But also here is a clear rank that those street signs that are sharp and clear images, they are then like in this end, and then this blurry nonsense, then they are less similar. And I should have included that as well, but we did the same for the ReLU activation function. And there was sort of no hierarchy. They seemed completely random what it gave them. So the rank did not make any sense, basically. So what I try to say is that in deep learning, it's not only about clever inference and clever scoring rules, but also about how to present your model structure so that it can capture what you're trying to do. So kind of the mantra in deep learning is that it doesn't really matter, just make it very flexible and fit it to the data. And that's kind of the wrong attitude I'm trying to say. Because the model structure you choose in deep learning, it still spans the family of functions that will represent your solution. And if that is somehow not representing what you actually want, then that's probably not a good thing. So we should pay attention to the architecture that we actually use. And stationary priors in these models, they can give a good proxy for capturing sensitivity or capturing like OOD things. And sometimes, in some cases, we kind of want this kind of opportunistic behavior, that we are fine with the model being very certain about things that happens outside training data. And that might be part of the success of deep learning models anyway. But then, if I sit in a car that tries to figure out the traffic signs that it's passing, I would kind of want the neural network model to kind of be uncertain about things. If it sees a traffic sign it hasn't seen before, it hopefully doesn't classify that into some class, but it would rather like admit that it doesn't know. And the current models aren't very good at this. And then, of course, like as part of the Bayesian deep learning community, that might like depends on who you ask, but I think that it hasn't been as successful as one would hope. So, so a part of that is actually being able to like encode meaningful prior knowledge into models, and I think this is a nice way of having meaningful prior knowledge. Good. Okay, so now I'm talking about models and capturing uncertainty in a useful way outside training samples. But then I'll also be working a lot in computer vision, and I learned to realize that people typically don't care about calibration in computer vision. This might come as bad news to some of you, but computer vision people, they aren't very interested in uncertainties in the first place, and definitely not whether the uncertainties are calibrated or not. And typically it's so that the uncertainty is just a proxy for something in a downstream kind of decision-making process. And thus I'm actually really happy that I stumbled upon this paradigm of dynamic neural networks. You might not have heard about dynamic neural networks, but it's basically the idea is pretty simple. The idea is to tune the computation effort to fit with how hard the problem you're trying to solve is. So say you have someone shows you a clear image of a cat, then you probably don't need a huge neural network to recognize the cat. You can do it with a smaller model. And only if the sample that is shown to the model is really tricky, then it kind of then like unlocks more capabilities step by step that also requires more compute. That's kind of the idea of a dynamic neural network. The problem here is that you need to somehow be able to, in an online fashion, decide whether the sample that is shown to you is easy, so that you can only use a tiny bit of compute, or hard, so that you need to unlock more compute to your disposal. And that is tricky. And the overconfidence of these neural network models typically lead to that it doesn't really want to unlock kind of more compute, because it's already really confident, and it has the small model that this thing here is a cat, and then it's just decided it's a cat, and then end of story, and bad things happen. So kind of our motivation here was to use some uncertainty quantification techniques to improve the online decision making inside dynamic neural networks. Of course, the problem here is that we need to do that without a lot of compute, because the whole point of dynamic neural networks is that you're very compute efficient. So that's kind of an additional tricky part. And what we did in this work was to present a computationally efficient approach for like post-hoc uncertainty quantification in dynamic neural networks. And we basically we use a Laplace approximation that then like guides the decision-making process as part of the dynamic neural network. So here's basically a setup. So we use a so-called MSD-net backbone, and we have an input. It's that image up there, and then the model consists of several blocks, where the first block consumes 7 million flops. And basically what we do is that we then apply like a post-hoc fashion, like a Laplace approximation here. We do it with like in a Kronecker factorized form to make the computational burden as small as possible. And then the model says that this is a fox with a 58% kind of confidence. And I know that it's not a fox. And also the model is so uncertain that we actually continue. And then we move to block 2, and that's like 40 million flops. And we do basically the same thing. We evaluate the predictive distribution here, and then we do something called model internal ensembling, where we actually use both the heads here from the model. And now it's 53% sure it's a tiger. And then we move forward, and then it's still like 53%, not very good. So then we unlock block 3, and then it says that it's 71% certain it's a tiger, and then we have a threshold of 70%, so we never unlock block 4 here now. That would then be a lot more. And then it would have been a tiger according to that block as well, but we never got that far. So this is the basic idea of a dynamic neural network. And then basically how this has been done before is that they just look at the logits of the model, and that's a horrible proxy for uncertainty. And this is still a horrible proxy for uncertainty, to be frank, but it's a lot better, as you will see in a bit, and it also works very well in practice. Good. Yeah, I have a slide about the Laplace approximation we employ here, and then there's a bit about the computational the burden, how many flop is needed per exit number. There's those like different blocks, and then we can do it either in a naive way, or then we can do it in a very smart way that actually doesn't add like in this scale of like 10 to the power of 9 flops. We can do it practically free of charge, the Laplace approximation here on top of this. And then I mentioned the model internal ensembling, so that we actually reuse the already calculated predictions from each layer then. Okay, so I have these plots here. These are all like really big image data sets, where we have basically now entropy here on the x-axis, and like a continuous error, not it's a classification problem. So this is basically captured from the logsheets for the vanilla model. So then if you look at kind of the easy samples, where the error is small and the uncertainties are small, they're basically they're typically images that are clearly sunflowers, bottles, oranges, palm trees, tanks, whatnot. Things that are even like visually for us humans easy to spot that. That makes sense. Then we have kind of this hard part, kind of where the uncertainty according to the model is big, and also the errors are big. So then we have things that are hard even for us humans to say what they are, and they are often misclassified here. It makes sense because if the uncertainty is also big, and that's fine. The model knows that it's uncertain about those. And then we have the bad part of the plot, where we have both mislabeled or ambiguous samples. They're, for example, it's a bit hard to see, but there's basically this image where there's a cloud and a rocket. And the true label is a rocket, but then it's being predicted to be a cloud. Well, that's also correct. But and then couch television, they're both the same photo, or then like seal, otter. I might mix those myself. There's a house with a palm tree in front of it. So should it be classified as a house or a palm tree, and so on. So it can be a bit tricky. So that's kind of the tricky part. And what we see, what we're doing, so we actually, compared to the vanilla MSDNet, so what we see is that we actually move in this plot. We push from the tricky part to the kind of good parts, from tricky to hard, basically, and that improves the decision making. And typically for these dynamic neural networks, the results are plotted in kind of these figures where kind of you have how much compute you use compared to then like accuracies. So here we actually see that both in terms of compute versus accuracy, we are doing really well. Even like in terms of accuracy. But then if you look at both the negative log predictive densities and the expected calibration error, we are actually kind of like orders of magnitude better than the vanilla MSDNet model. And of course, if we can capture the uncertainties of the model, the decision-making process also improves, and that kind of makes everyone happy. Good. Yeah. So then we did the same for ImageNet as well. Lots bigger data set, bigger images, more compute needed, and the effects are like as clear there as well as in the smaller image data sets, which is very nice. Good. Okay. So this was an example where in computer vision, actually people care about uncertainties and care about calibration. So and I learned that typically in more these applied fields, these cool things are only considered cool if they actually are useful for some end purpose. So we would like to have both a prediction and an associated uncertainty. But then most people don't care about getting that uncertainty, they just want to have a better prediction. So if you can actually improve the predictions with uncertainty, that makes people in these applied fields much more happy than actually giving them a measure of uncertainty. Good. Okay, I'm almost out of time. We have codes, resources, more things available online on GitHub, and then there's even some videos related to these projects on my website. I'm happy to discuss in the remaining 2 minutes that we have here.
Thank you very much. for this great talk. Questions, I'm sure. Yes.
Yes. Thank you for the great talk. It was a pleasure to listen to it. So, first I wanted to clarify a couple of small things. When you mention uncertainty for the confidence for the neural networks, do you mean just the entropy of the after its softmax layer?
In some plots it was the entropy. In some cases it's the predictive standard deviation. Then.
Okay, and also when you were talking about Laplace approximation, it was this Laplace redux type of thing from Tübingen. Okay.
Yeah, exactly.
And yeah, then a sort of question comment. I want to pretend for a moment that I'm the deep learning cat from the beginning of your talk, and ask about stationarity. So a way I like to think about stationarity is that this is the property that makes sure that if you translate your data set, then the model trained on the translated data set is just a translated model. And there is a reason perhaps why deep learning people don't care about this, because rather than making sure that the model translates according to the translation of the data set, they just translate the data set in a canonical way. So in this way, is the stationarity really that important to enforce in deep neural networks? Or we can be better off just doing this simple engineering thing?
That's a really good question. And maybe the thing is that, which also kind of shows in the results, is that the stationarity is not that important, because the locally stationary model that I first derived that has this assumption of an input density. So then it's actually not truly stationary, because it has these envelopes that kill off the actual stationarity. But so then the model learns to leverage kind of the properties of the model functions, and it basically works equally well as the globally stationary model. So it's rather than actually the stationarity, it's kind of the properties that when you move outside the data, then you get kind of diversity in the model functions that helps there.
Basically, uncertainty grows when the distance grows.
Yeah.
Thank you.
So it implicitly learns that. Yeah. So you're right. Kind of the translation invariance per se is not the key.
So I have a computational question on the computational side. So with these random neural networks, have people or have you looked at low precision, mixed precision? Because I mean, you can obviously, you don't need these to be very accurate. You can go to very low precision. No?
Yeah, that's a really good question. Now, I haven't looked for this. I worked with like low precision models for other things, but not under this.
I mean, some people in our university, they even use logicals. I mean, just
-1,
1, 0.
Yeah, and that, to my experience, I have one student who is working on related things. That typically works really well.
SDEs, we have used instead of Gaussian increments, you use like discrete ones.
Yeah.
And they work quite well too. So.
Yeah, that's really interesting. Yeah.
I finished this side and I promise. So,
can you say anything about the first part? What happens when you actually train the model with gradient descent, say?
Yeah, so like the results I showed, they were actually trained with
Well, sorry.
Yeah.
I think you were training the last layer, is that possible?
Yeah, so in most of the experiments, we kind of, we trained the whole model, but then we basically treat the preceding layers as kind of a feature extractor, and then we have these activation functions on the last layer.
But that's what, if I understand correctly, correct me if I'm wrong, that may be called random feature model, right?
Yeah, kind of, yeah.
Right, but when you actually train the rest of the model, then the kernel changes, right? And then, do you know how your results extend to that case when the kernel changes?
So we've also tried so that we have this activation function on all layers, and then we train everything jointly. And turns out that it also works, just slower to train because the activation functions aren't as nicely behaved. But then it's still a non-linearity, and the model still adapts to what it can do, and it still works equally well.
And you have a proof of that?
We tried that then with this, yeah. It's just more painful to train because it's not as well behaved.
Yeah, regarding this connection between activation functions in neural network and the kernel functions in Gaussian processes, I think it was on slide 16. So the one you say is the limit when the width of the neural network goes to infinity. So then I was wondering whether the other direction is also unique. So when you fix a kernel and you look for the corresponding activation function, can we say the corresponding activation function, or couldn't there be many which have the same limit and therefore correspond to the same kernel function? I mean, the other direction, yes, sure, but the inverse, so to say,
Yeah.
it's not immediately clear that this is unique.
I think you're right. Yeah. I have no further comment on that, but I think you're right. Yeah.
Okay, so my question is similar to the first one regarding the stationarity of the kernels. If it's okay, let me rephrase it. So if the stationarity isn't that important, is it about the spectral decomposition about the kernels? So because there are also non-stationary kernels, and I wonder if you could also construct activation functions with non-stationary spectral kernels.
Yeah, I think so. Yeah, and of course, like the spectral representation, that's just like one way of representing the problem.
Yeah.
You can represent it in many ways, but it's kind of a convenient way to deal with these. Yeah. So yeah, definitely. Yeah.
So on the first part, yeah, so you show nicely, and you had a question about that bridge between GP and kernels via Bochner theorem or Wiener theorem. Now, if you look at another view with GP explanation, if I can say, of neural network, like the neural tangent kernel, which is very different in spirit.
Yeah.
Yes. But still, I mean, what if you bring your machinery and consider a neural network which is based on your right activation function linked with GPs that you know, covariance that you know? I mean, is it possible to improve, I mean, the understanding of what we get from the neural tangent kernel, which say that a neural network can be seen after training as a GP with a specific kernel based on the rating of the function.
It's kind of like a very different different
exactly.
direction.
Absolutely.
And yes,
That's
like definitely there's kind of like ways of analyzing that, but then I don't have any magical wisdom here. But I think it's a really interesting kind of direction. Like I have a student who has been looking at that a bit, but there's nothing out yet. Yeah.
Thank you.
A very good question. Yeah.
Thanks a lot. Other questions? Yes.
In the dynamic neural network model that you study, is there anything that measures the difficulty of data instances? So with some represents it with some, I don't know, like norm or something, that we can predict how much into the network we should process it.
Yeah, it's basically, yeah, that's kind of what the decision making is based on. So then kind of then how difficult the sample is estimated by the uncertainty related to the prediction. So it's like the Laplace approximation on the output from each head of the network.
So it really depends on the network itself. Is it possible to say it from the data itself, some property of the data instance, how difficult it is, some measure of difficulty?
So yeah, kind of like I'm not sure if I get the question, but yeah, like the samples passed to the network is kind of for the network then to realize whether the sample has been passed in is difficult or not, or how difficult it is. So it's kind of part of the modeling. I'm not sure if I actually managed to answer the question.
You can chat after.
Yeah.
Okay, very last question. and then you...
So when you compare to standard deep learning models, do you do simple things like to calibrate them a little bit, right? Like temperature scaling or task scaling, kind of make it kind of more like comparison, or is it just the train run that we are doing?
Yeah, basically in this work, not really. And then like we also used, in the paper we used many different ways of doing inference, because then like for smaller models you can actually do like, you could like do sampling and then like get some better results. But then we used like Laplace approximations and other things to then like do inference in these bigger models to compare. And it's kind of then like, that's like kind of a orthogonal thing than all the other things that you can do for like, you could do temporary, you could do almost anything kind of on top of this. This is basically more of the modeling part, like what you want to encode into the model. So then like all these things you can also do.
Okay, that answer, we thank you guys.